In the last lesson we learnt that covalent substances can be classed in two ways. They can either be simple molecular substances or they can be giant covalent. In this lesson we're looking at the giant covalent structures. Now, giant covalent substances can be elements such as diamond, which is made from carbon. There we go, that's the carbon atom. Or it can be a compound such as quartz, which is made from the silicon and oxygen atom. So here we have the silicon atom, and that's joined to two oxygen atoms. So here we have this silicon dioxide unit, which is repeated throughout the giant covalent structure. So the formula for quartz is SiO2. Now, these giant covalent structures are similar to the ionic structures that we looked at in a previous lesson, except that they are not made from ions, but they're made from atoms, which are joined together not by ionic bonds, but by strong covalent bonds. So we have atoms which are joined by strong covalent bonds. Now, as a result, these structures have very high melting points. Okay, both the melting point of diamond and quartz is very high, and because these are atoms, not ions, held together by strong covalent bonds, the giant covalent structures are not soluble in water. And for the same reason, because there are no ions present, there are no free charges which can move between the structures, they don't in general conduct electricity. So that makes them good insulators. There is an exception to this, which we will look at in a minute, but one more thing we should point out is that because these structures are held together again by very strong bonds, they tend to be quite hard as well. So diamond is in fact one of the hardest substances known, and quartz also is a relatively hard substance. Now, I'd like to take a closer look at the structure of diamond. As you can see from this diagram, diamond is made from the carbon atom. Now, remembering the dot and cross diagrams for the carbon atom, well, carbon is in group 4, so it has 4 valence electrons, like most of the other elements in the periodic table. It wants to obtain stable octet structure, and to do that it's going to form covalent bonds with other carbon atoms. Okay, so each of these electrons is going to combine with another electron from a different carbon atom to form a covalent bond. Let's just have a look at that. So you can see that this carbon atom is sharing its electrons with this carbon atom here to form this covalent bond, and likewise here it shares the electrons with this carbon atom, and these carbon atoms will then go on and share electrons with other carbon atoms, and the whole thing extends over this giant covalent structure. Now, in the dot and cross diagram in this case is represented on the plane of the paper, but this is in fact really a tetrahedral structure, so it looks more like this. Okay, so we have the carbon atom joined onto these other 4 carbon atoms in a form of pyramid. That's say what we call a tetrahedral structure. There you go, a tetrahedral. And this tetrahedral structure is very stable indeed. It's a very stable structure, and as you can see in the case of diamond, this tetrahedral structure goes on repeating itself over and over again, and it is precisely this that makes the diamond such a very, very hard, very stable structure. Now, diamond is what we call an allotrope of carbon. Now, an allotrope is really just a different form of the same element. Now, another common and very useful allotrope of carbon is called graphite, and in graphite the atoms of carbon join together in a slightly different way, which give graphite some very interesting and useful properties. Now in the case of graphite, what happens is this. 3 of the valence electrons of this carbon atom, that's this one, and this one, are shared with the valence electrons of these 3 carbon atoms to form covalent bonds. Okay, there. Again, this one will share with another carbon atom, and this one will share with another carbon atom, etc. Alright. So what we're saying is that these 3 valency electrons here are used to form covalent bonds with other carbon atoms in this hexagonal structure, okay, forming this plane of carbon atoms, while this 4th electron is not used to form a covalent bond and is effectively free. So what you get is a structure with planes of carbon atoms arranged in this hexagonal structure, which are able to slide over each other, okay, on this sea of free electrons. These are provided from this 4th electron, which is not used to form the covalent bond. And this sea of free electrons makes graphite a very good conductor of heat and electricity. In fact, it's the only non-metal that conducts electricity. And in addition, because these planes can slide over each other easily, it also makes it a very useful material for making pencils. Right? Pencils are made from graphite, and what happens is when you draw your pencil over a sheet of paper, the friction between the paper and the pencil leg causes these planes of graphite to fall onto the paper and enables you to write on the paper effectively. Likewise, the ability for these planes of carbon atoms to slide over each other due to this sea of electrons that lies between them makes graphite a very good material to use as a lubricant. It helps to reduce the friction between 2 moving mechanical parts.